So we just said, how can we make our estimates better for integrals? And we said make then boxes narrower. So here we can do that. I've got the step size, the width of each box set to 0.25. And this is a complicated way of saying what's the total area under the curve according to those boxes. And as I bring this step size down, we're doing narrower and narrower boxes and more of them. What's happening to this total area of all those boxes seems to be getting smaller. And right now it looks like a pretty good approximation, right? We can barely see those box heights, but we can still kind of see them. Let's give ourselves a bit more room here. How about, we'll say we can take steps that are even smaller. You can see this is kind of a pain to negotiate in Desmos. But now I can make the steps even smaller. You see those boxes are getting narrower and narrower. And we could be kind of keeping track of what that number is doing as we change the box width and everything. Right now I'm using the right end rule, but we could use the left instead, or even midpoint. This formula, this file is set up to allow us to change which side we're using. I copied this file from someone else who had originally written it in Spanish and then made my own improvements, but I left the original Spanish comments in there. So there was a pain to kind of have to adjust the slider range and everything. And as I changed stuff, I didn't get to keep track of that in any formal way. I was just kind of thinking about it and trying to remember it. So we could do this in Excel, but the problem with Excel is the more boxes you use, the more rows you need. You need basically one row for each box. And so doing narrower boxes, you end up needing more and more rows, and extending the number of rows each time is a big pain in Excel. So the right tool for this job is a programming language where you can just tell it do this many times and it'll do it, and you don't have to set a new row for each thing. I'm going to use Python, which a lot of engineering people use these days. It's a lot like MATLAB. Stats people would use a language called R, but I'll share the link to this Python file online. We import some libraries that we'll need. Then we define what function we want to integrate. We could integrate sine. The book uses a formula for its main example of 4x minus x squared. But we've been using just x squared. So this is like saying f of x equals x squared in Desmos. And we say, let's start at x equals 0, stop at x equals 1. Let's use 4 boxes to begin with. And then how big is each box? What's the delta x? Well, if I have to go from 0 to 1 in 4 steps, that would be 0.25. So 1 minus 0 divided by 4. Ignore that for now. And then I want to say let's keep track of the sum of my box areas so far. So I'm going to start my summation at 0 and like how much I've accumulated so far. And then just do a for loop, I equals 1, I equals 2, I equals 3, I equals 4. Figure out the x value for each box, and then plug in that x value here and get the function value. Multiply by delta x, that gives us the width of that box, the area of that box, and then add that to my running sum. So if I run all that, I get 0.21. We're using the left-hand rule here, so we're getting a lower bound because of the shape of the function. So I could go back and change n and get a new answer, and change n again and get a new answer. But the nice thing about a programming language is we can write a for loop to do that. So here I've put this summation thing where we set the sum to 0 and then loop over each of the boxes. I put that in its own function where I can tell it what function I want, where to start, where to stop for x, and how many boxes to use. And then I can call that over and over again with different values of n. Here I wanted to have n increase quite a lot, so instead of saying n equals 4 and 5 and 6 and 7, I wanted to use, let's use n equals 4, 8, 16, 32. So I'm just using powers of 2 here. 2 isn't anything special. It's just It increases reasonably quickly, but not as quickly as 10 to the n would, which we just don't need that kind of power. So this is telling me with 2 boxes, here was the total area of those 2 boxes. With 4 boxes, here was the total area of those 4 boxes. This is all integrating from 0 to 1 x squared. And you see a pattern, what's happening here as I do more and more boxes, each of them being narrower and narrower. Does it look like we're converging on anything? Anything familiar? So that's kind of handy. We can do that using a programming language. Here, this is a programming language tip. I'm just printing the results, but I'm not storing them for later use, which is actually a bad idea. It's nice and simple though. In the box down here, I show a way to store them for later use by storing them in a pandas data frame. And then we get this, and we can go analyze like how is the error decreasing as I add the number, as I add more and more boxes, which is kind of a fancier thing to do. But I didn't want you to think that just printing them out and then forgetting them the next loop around is the right thing to do. So that's us using a programming language to try more and more boxes, each of them narrower and narrower. And now let's try an equivalent thing with paper and pencil. So let's look back at the sum we had written for the total box area. We had the height of a box times the width of a box plus the height of the box times the width of the box, etc. And we went and did that in a programming language, which is great. The problem with that is we could try different numbers of boxes and different widths, but we didn't have any formulas that would let us say, well, what if I let n just be super duper large? What if I let n be infinity? N is the number of boxes. So we want to turn this into a formula that we can write involving the number of boxes, and then say, what if that number of boxes zooms off to infinity, and get a formula for the answer, because even programming languages can't really do that for us. So we want to turn this into a formula. So we're going to turn it into a formula. But we need a new kind of formula that says take the sum of a bunch of things. And the way we're going to do that is to say a big summation sign like that. That's called a Greek sigma, S for sum here. And I'm going to say I equals 1 to 4. This will be box number 1, box number 2. So this area was box number 1. This area was box number 2, etc. So we're saying let I start out at 1 to talk about box 1, and then we'll do I equals 2 for box 2, and I equals 3 for box 3, etc. So we're saying I equals 1, 2, 3, and 4 here, because we're saying I stops at 4. And what is the x location that I'm using here? Well, when I was 1, it was 0.25. When I was 2, it was 0.50. When I was 3, it was 0.75. So in general, I could write 0.25i there. And then we could try to get fancy here, or we could just say these were all the same. Let's just call it delta x. And off to the side, we'd say delta x equals b minus a over n, where n is the number of boxes. So again, let's say this symbol is a sigma. It's a capital Greek letter. You might have seen a sigma before written like this in like standard deviation, and that's a sigma in lowercase. So this capital sigma in Greek letters means summation. So it's the S in sum is making us think of other letters that are basically S, and so that's what we use. Remember, we said in integrals, the integral sign is basically an elongated S for summation because it's related to all this stuff. So this is a summation sign. I is called the index, and it's sadly not related to the square root of -1 like imaginary numbers. And this summation is the equivalent of a for loop in programming. And if you don't know programming, that's okay. It wouldn't hurt to learn, I guess. We won't be requiring you to do any programming in math120. At least not Python style, Excel kind of. So this is equivalent to a for loop in programming languages. So we said like my sum equals 0 for I equals 1 to 4. And we did basically my sum equals my sum plus f of 0.25 times I times delta x. That's not exactly what we had written in Python, but that's kind of the meaning of what we had written. And let's take another look at it. We'll talk more about summations separately. Writing this, I equals 1 to n, however many boxes, of some function height times some box width, or interval width, you could say. We're saying that that is computing the integral a to b of f of x times dx, as long as you let n be very, very large or go to infinity. So that's the idea of Riemann sums. And it's analogous to the way we write integrals with a function height times a dx value, which is a very, very skinny box width. All right.